Welcome. While renovating our bathroom at home the whole week, I was thinking a little bit about a general problem, how to define an n-particle system on a geometry. And what we want to have is that the particles interact in the most natural way possible. It should be deterministic, it should be reversible. A single particle should move on a geodesic. We want to have a local interaction, a cellular automaton rule. We want to have it natural. We want to have it defined in the simplest possible way. Maybe just measure the number of lines. We can implement that. Actually, at the moment, I have about 5 lines to implement what I suggest to do. So first of all, we have the geodesics, which are motions, free motions on the simplicial complex, finite abstract simplicial complex. We assume we have a manifold structure or manifold with boundary structure, meaning that if you look at the wall, a Q-1 dimensional simplex, it is either a wall on the boundary, then it has one Q simplex which is attached, or it is a wall in the interior, and then we have 2 simplices of dimension Q attached. So simplest example, 2-dimensional discrete plane is the hexagonal lattice. That's the lattice I was contemplating when renovating the bathroom. So this is the shape of the tiles, and we have geodesics moving there freely. If a single particle is there, it should just move freely, like Newton's first law. And then we have to think about how do we implement the interaction in the simplest possible way. One of the things which is natural, I think, also in other contexts, is to look at a divisor as a particle structure. So a divisor is just attaching to every maximal simplex. It attaches a number telling how many particles there are. And if it's negative, we think about them as negative particles. So we have positive particles, negative particles, and we have a rule how they evolve. And that rule is the geodesic flow. Both move on geodesics. It's just one turns in one direction, the other turns in the other direction. Remember how we did the geodesic right here? We replace the first node, we replace with an opposite node, and then we just rotate. But we can rotate right or rotate left, and so this depends on whether we have positive or negative particles. And then in the context of divisor, the total number here, this is called the degree, so this is n plus minus n minus. So we count the negative particles negative, the positive particle positive. You can also write it like that, right? We have just n plus particles of the positive type, n minus particles of the negative type, and then we let them move. They move on geodesics, but if they are alone, if they come together, what happens is we just change the geodesic law at points when they are collisions. And what we do is we just add up all the particle numbers and we rotate by that number. So that is kind of just compatible with a single motion. It's the simplest possible motion. You can think about more general interactions, because the symmetry group, I mean, this is a principal, we have a principal bundle, right? Fiber bundle over the facets, which are the oriented facets. So this geodesic flow is on the oriented, it's like a moving frame. And what happens is the order matters. We want, this is a non-abelian group, right? The SQ plus 1 is non-abelian. Yeah, this is a principal SQ plus 1 bundle, which is non-abelian. And in order to have an interaction which is abelian, meaning that if you take 3 particles coming together, then we want to have that the motion doesn't depend on when they come together, which is already a problem if you look at 3 disks, right? The hardcore model, when you look at that, when you take 3 particles coming together, it really depends whether you take first the interaction of the first 2 and then interact with the third, or if you take the second and third and interact with the first. So there are different outcomes of this billiard collision of 3 billiard balls. We want to have a deterministic, clear outcome, what happens. And I think that's kind of the simplest thing you can imagine. Right? You just add them together, you add together how many particles you are, and this tells you then, whether you rotate, how you rotate in that frame bundle. So the interaction only changes the orientation of the frame bundle. It doesn't do anything else. The other law, we can write it as a product of two laws. I like that Coxeter description, that we have two involutions. We can write it as a product of two involutions. We take three particles, one, two, three particles, and these three particles are given just by ordered simplices. They have 3 point particles, and they move. They move according to the geodesic law, which I described for several weeks already. They move here, and what happens is that tile here, they come together. Now what happens is very interesting in this case. So what happens is that at this point now we have 3 positive particles coming together, which means we are rotating by 3 here, meaning rotating by 3 means not rotating at all. So it's kind of a game we can play and see whether this is interesting. I have to make experiments and see how that works. And we can take also many particles. We can even take space itself as a particle configuration. Right? If you take space itself, we take at every facet, we choose one particle, and then we can see what happens when we let them, we let it evolve. We could even think about that we have a boundary thing, like in the novel of Egan, the Shields Ladder novel, the hardest novel is. I never finished that novel, it's too hard. But so in that novel there is a Sarumpite rule mentioned, kind of a universal rule, which is kind of like a discrete relativity framework. And in some sense what happens is in general relativity you don't have any kind of interesting interaction between geodesics. What happens in general relativity is that the geodesics, the particles move on geodesics, but they influence by the Einstein equation space, and so indirectly influence each other, which is a very difficult problem already for a two-body problem. While Newton's problem here is no issue. That's Kepler solves that already in the case of 2 bodies. 3 bodies is very hard. N-body problem, one doesn't even know whether there are almost everywhere existence of solutions, because there could be escape singularities of positive measure. One doesn't believe that, but it's not known whether they escape singularities. Particles going to infinity in finite time have positive measure or not. It's one of the problems of Simon. Here is really a problem when the particles collide. So any framework where you use the Laplacian, where you use the green function of the Laplacian to get the potential, is a problem. Also on graphs, if you look at that. But then there is also in the discrete a problem that we don't have any differential equation, right? Because we are jumping around. We have not a differential equation. We are moving stuff around in a discrete way. So we have to have rules. We want to have rules. Cellular automata are natural, but cellular automata are just lots and lots of cellular automata rules. And it's like in plumbing, or what I was doing this week, plumbing and tiling and floor renewal. And so there are lots and lots of decisions, lots and lots of problems, lots and lots of choice. What type of tile do you use? What type of floor do you use? How do you repair things? And so there are lots and lots of choices. And if you have a lot of choices, that's not nice. You want to have something inevitable. You want to have something like this Sarumpite rule, which is, which anybody in another galaxy would come up with naturally as the first possible choice of motion. Now I think the geodesic flow is very natural, that works very well. The interaction here, you have still possibilities to make this more maybe interesting, I don't know. Just a game we can play and see what happens when we let n particles move on a simplicial complex. And that's it for today.